Good afternoon and welcome to this third live session for the course Viscous Fluid Flow. So if you have any questions and doubts, you may post it in the chat box. So if you have any questions, please post it here. Okay, so in the meantime, I will just discuss some questions from the discussion forum, which actually you have posted in the discussion forum of this course. So in between, if you have any doubts, you please post it here. Okay, so one question was asked from this slide while calculating the penetration depth for flow due to an oscillating plate. Okay, so you have seen that flow due to this oscillating plate, we have the solution u by u naught is equal to e to the power minus root omega by twice nu y cos root omega by twice nu y minus omega t. Okay, so this is the velocity profile u, which is function of y and t. So if you want to calculate the penetration depth, that is your at a particular time, that means instantaneous, then from here you can see that we define the thickness delta of the oscillating layer as a position where u by u naught is equal to 0.01. Okay, now your question is why 0.01? Okay, so it is actually it should be means very small. So but in practice, say to identify that very small, it is very difficult. So we tell that if it is u becomes 1% of u naught, then that we just tell that it is the penetration depth. And similar way we defined, if you remember, for the boundary layer thickness, right? So u by u naught, that's why we are taking just 0.01. Okay, and now the next question is that maximum cos value is 1. Exponential term can be anything in the UIT function on previous slide. So you can see that when you are defining the penetration depth, so obviously you see this is the problem, right? So this is your Stokes second problem. So this is the plate, okay. It is oscillating like this, and you have a stationary medium. So obviously you can see that it will penetrate, okay. So at a particular time, maybe it will just one velocity may look like this, and you can see that we are interested when we are defining the penetration depth, that what is the maximum length it can go, right? So that is the penetration depth. So when we are considering this cos, this term, then obviously if it is 1, if we take, then we will get maximum y. So in this case you can see that delta becomes, I think 6.5, I think delta becomes, I don't remember exactly, it is 6.5 times root nu by omega, okay. Now you are telling that it may vary between any value, right, 0 to 1, but we are taking the maximum value such that this penetration depth becomes maximum, okay. Say if you consider, say, this value as 0.5, let us say that this cos value it is becoming 0.5. So in that case, so your delta, if you calculate, it will become almost 5.53 root nu by omega, okay. So this is your this cos function 1 if you consider, and in this case it is 0.5, okay. So obviously you can see that it is lesser than that, okay. So obviously the maximum value whatever we are getting, that we are considering, for that reason we are considering this cos term as 1, which is your maximum value. There is another question that why cannot those large turbulent eddies retain their size in turbulent fluid flow? Why the breakage of larger eddies into smaller one is necessary? So obviously you can see that when we define the turbulent flows, it is a large Reynolds number flows, and we have much inertia in the flow. So obviously turbulent causes the formation of eddies of many different length scales, and most of the kinetic energy of the turbulent motion is actually contained in the large scale structures, okay. And this energy cascades from this large scale structure to smaller scale structures by an inertia. So you have an inertia effect, and due to that these large turbulent eddies actually split it into smaller eddies, and kinetic energy is divided, and that way you can see this process creates structures that are small enough that molecular diffusion becomes important, and so viscous dissipation takes place, right. So due to this inertia term, actually these large turbulent eddies cannot retain their size, and it actually split it into smaller eddies. Another question was asked that as there is finite distance h, how does this conclude to a cos hyperbolic function? What am I missing here? Earlier plate flow case we use general solutions according to integral solution, then why cos hyperbolic here? So you can see that in this case it is a Stokes squared flow, that means the upper plate is oscillating, right, with u naught cos omega t, and bottom plate is stationary. So obviously you can see that with time the velocity profile will change. How it will change? So obviously it will determine by this function, and you can see due to no slip condition, here if you consider one point, so this fluid particle will remain here, but due to the oscillating plate, okay, sometime this velocity profile will look like this, or it will look like this, okay, and different time instances it will vary, right. So now you can see that if you see the velocity profile, okay, at a instantaneous velocity profile, okay, at a particular time, if you want to see the instantaneous velocity profile, So obviously it might become some exponential things, because these functions, hyperbolic functions, cos h plus sin h with some constant if you have, so obviously it is representation of this exponential function, right? So the velocity profile you can see, so it will be looking like this. Okay, it is not kind of parabolic, and you can see that this when we have a finite length, that time we write the solution in terms of hyperbolic function. Okay, so this you should know, means when you are solving some heat conduction problem or fluid flow problem, and if you have a finite length in that direction, then you write the solution in hyperbolic function rather than in exponential function. If one direction is infinite, then you write the solution in terms of exponential function, so that you get the solution simpler. Okay, so that's why we have written the solution in terms of hyperbolic function. Next, another question was asked that what is the difference between non-dimensionalization and scaling using order of accuracy. Okay, so obviously you can see that when we use order of accuracy for scaling, so we do some actually order of magnitude estimate for any quantity, and we generally consider for quick and theoretical calculation for any quantity, and we can actually estimate which is actually smaller and larger. So smaller, if it is very smaller compared to the other one, other terms, then we can neglect, okay, comparing these estimates. So in that way we use the scale analysis, so it gives very quick means some theoretical analysis. Okay, and when we do the non-dimensionalization, obviously you can see that we write some characteristic either length or characteristic velocity, right, or characteristic time. So that way we express the governing equation, full governing equation in non-dimensional form, so that we reduce the number of parameters in the equation, right? So if you see the governing means this momentum equation with suitable this characteristic parameter, characteristic velocity and characteristic length, you can actually write the coefficient of diffusion term as 1 by RE, where RE is the Reynolds number. So you can see that in the momentum equation, if you use non-dimensionalized equation, then you have only one parameter. But now in Reynolds number, we have actually clubbed rho u L by mu. Okay, so where rho is the density of the fluid, u is the velocity, characteristic velocity, and L is the characteristic length, and mu is the dynamic viscosity. So all these parameters we have clubbed together, so we have reduced the number of parameters. So now if you vary anything of this, if you vary the fluid, or if you vary the inlet velocity, or if you vary the characteristic length, let us say diameter of a pipe, so if it is a pipe flow, then but only one parameter you can change in the solution or governing equation, that is your Reynolds number. Okay, so varying one parameter actually it will represent the variation of all these properties. Okay, so obviously it will be easy for the representation of the solution, so that other researchers may use readily your solution. Okay, so that is the way in which we do the non-dimensionalization. Okay, so there are no questions. I can see that it is posted. So if there are no questions, then we will just close the session. Thank you very much for attending this live session, and if you have any questions, you please post in the discussion forum. Thank you very much, and all the best.